No, I mean,
It's not cheating.
No,
There are no rules applied.
yes, there are.
There are rules. There are no rules applying to other people helping other people.
All right, questions on the homework. We have a quiz on Friday over stuff here in chapter, actually all of chapter 6. Chapter 6 is only these 3 sections. Any things you want to look at? A lot of the quiz comes from this section. I mean, being able to, and it really expands on the things we learned in the last section. I don't think there was any Simpsons rule in the homework, was there? I mean, you need to be able to do a Simpsons rule. It's just that we don't have an error formula for Simpsons rule. Interestingly enough, Simpsons rule is at the end of the chapter, and we're not going to talk about it, but Simpsons rule does have an error formula and involves the 4th derivative. The 4th derivative. You know how a left and a right will fit a constant function perfectly, and a midpoint and trapezoid will fit a linear function perfectly, and we said that a Simpsons rule, I think I told you that, would fit a parabola perfectly. It turns out that it also fits a cubic perfectly. So it takes the 4th derivative to involve the error on Simpsons rule, which is one of the reasons it's so much more accurate. But anyway, so you wouldn't have an error formula for Simpsons, but you still have to be able to do a Simpsons approximation and be able to write it out. All right? So, anyway, back to my question. What questions do you have? You want to check some answers or 30? Okay. Before we do 30, I would like to do a different one, but we definitely will look at 30. In the other class, they just wanted to hear a few answers, so I thought we would talk about that just a little bit. For example, on 9, what K, on 9b, what K1 value did you have? Because the K1 values that they put in the book, or the K values they put in the book, they didn't always make the best choices. What did you guys have on 9b? 0.5. That's what they have in here. Okay, did it come out exact? I think it might have come out exact. And then on C, what did you have for K2 there? 0.75. And again, I think that one came out exact. It doesn't happen very often, but you know, your max of F prime, max of F double prime. Okay, 0.75. All right. So on 11, how many rectangles did you have there? 773. It would actually round up, and that's if you now they well. Here's the thing: they used a K value of 0.8578. I think the K value was 0.8577 something. So they did 0.8578. I think if you did 0.86, that would be fine. 0.9 might be not as good. I think 0.86 would be useful. So anyway, they had 772 point something, so 773. Now, but again, depending on what your K value is, right? Now, if you did 0.9, you might have got a different number. But it should have been in the ballpark anyway. 12, what about 12? What do you have for K1 there?
14.
For what did you use for K1? 3.59? In that ballpark? I mean, okay. So now they used 4, which would be a bad K. I mean, 3.5 should not round to 4. So they had 1,600. So I'm guessing a 1,400 range somewhere in there, like you said. Sounds right. 13, they had a K1 value of 0.65, is what they say here. So that would make 65. It would take 65 rectangles for that. Okay. Nothing else? I mean, if there isn't anything else, we'll just talk about 30. That's fine. But, you know, make sure you write them out. Make sure you understand about writing out a T4 or an S4, an M4, L4, how you write that out and all that stuff. Use your calculator then, of course, to add it up, do the calculation. That's great. okay, well, in 30, and maybe you missed this, 30, you were supposed to look down at the graph at the bottom of the page. Did you recognize that, the directions? Okay. So, what is that graph down there on 30? Of f, right? Which means it's what? Means that graph is what? I don't think I've heard it. Maybe you said it. What is that graph down the bottom that you're supposed to use for problem 30? That's f prime. That graph is f prime. Since f is the antiderivative, then that means that graph is f prime. And in the problem 30, you need a k1 value, right? Because it's a left rectangle approximation, so you need a k1 value, which means a max of f prime. Well, but it's the absolute value of f prime. So looking at that graph, where are we looking at on that graph? The lowest point at the far left edge when x is 0, and you would use what? 9 would be a reasonable number to use based on the graph. So the idea on that one is just what we talked about yesterday, is we want the max of the absolute value. If you don't do the absolute value, when you look at your graph, it might be a negative value, but you use the positive value. So you would use a k1 of 9, so it would look like this. So you would say, okay, k1 of 9, that goes there. You'd have 4 minus 0. And since this is a left, this would be squared. And then all over 2n, and we want that to be less than or equal to 0.0001. Correct? So, alright, so you just solve that. Go on your calculator and solve it. And it came out to be n is greater than or equal to 720,000. Okay? Now, why so many? I mean, I might ask you something like this. I mean, I want you to understand the concept of what's going on. Yeah, the calculation's important too. But why so many? Well, they're left rectangles, and left and right rectangles are notoriously bad, estimators. Unless you have a ton of them. And they want us to get all the way to 3 decimal places, right? But that's still a lot of rectangles, Zach.
Would it be because the slope's so high?
It's not, you have to go a little deeper than that. That's part of it. The slope is 9, right? We use the K, remember, what do we do with that K1 value? When we say K1 is 9, what are we doing with that 9?
So it's straight out for the whole
Well,
slope.
yeah, okay, keep going.
The whole slope, so it's constant.
Yeah, when we pick that K1, we do a worst case scenario, right? And we assume that the graph had a slope of 9 the whole time. So just the fact that it's 9, though, doesn't make it, and just the fact that we assume it's 9 the whole time doesn't really mean that yet. You're missing something. Look at the graph again. Look at the graph again. Well, yeah. Alex?
Is it because it starts at 9 but it goes all the way down to 1?
Okay, what if that graph right there was down there at -9, right? And just kind of stayed down there around -9. We would still have a K1 of 9, right? And would anything change in the formula here? You get what I'm saying? Okay, so you got a 9 here. This says you need 7. I guess I should word my question a little better than this. It's not, I mean, what you said is right. What Zach said is right. The fact that it's a big number, the 9 is a big number, ends up making this big here. Okay? I guess what I'm interested in is, remember how this is the max error, the worst case scenario, that we need 720,000? How many will we actually need, right, do you think? And that's where Alex is, and that's kind of what I meant by that, and that's what Alex is getting. If you look at this one, it's not 9 very much, right? The slope's not 9 very much. What if that graph would have run along and stayed around 9? We'd have still had the same calculation here, still had 720,000. Would we have needed all 720,000? Pretty close to it. If the graph had stayed down around 9, that would have been saying, hey, the slope is around 9 most of the time. And that's what we were assuming, right? We're assuming that the graph's going to have a slope of 9 the whole time. So if it actually did have a slope of 9 most of the time, or down in that area, then it would probably take all 720,000 of these. But looking at that picture, the slope's not 9 very much. So that tells me this is going to be way more than we need. And we're probably going to get 5, 6 decimal place accuracy maybe, or better, right? You see what we're getting at? So I really want you to understand this idea of, when we pick this K1, we're assuming it's going to stay that slope the whole time. But it may not be. And how much it varies from that, it will determine on whether these are really going to be needed to get that accuracy or not. But it will guarantee, at least we know that 720,000 of those left rectangles will guarantee the accuracy to 3 decimal places. Okay, so that's what was going on number 30. All right, well that's good. If that makes sense to you, then that's great. Let's move on then to what I want to do today is just give us a little background that's going to help us hit the ground running tomorrow when we do section 6.3. So we're going to review just a little bit here about differential equations, because section 6.3 seems on the surface like it is completely unrelated to what we've been talking about in the rest of chapter 6. Now hopefully as we go through it you'll recognize, and I'll try to point some of that out today, that it is actually related to what we've been talking about. So there is a method to their madness in why they put it in this section here. Okay, so far what we've done in chapter 6 is we've said, okay, let's look at our approximation techniques, because some integrals can't be found exactly. So let's take a look at our approximation techniques and let's investigate why they're off, how accurate they are, and what would cause them, how we can make them better, and all that good stuff. And how can we approximate these integrals and get fairly close using approximation techniques. Okay, so if we go back to what we learned about differential equations, and that's what this last section is going to be about. Let's look at what we've done so far. Okay, first of all, what is a differential equation by definition? An equation with a derivative in it. That's it. Okay? What is another thing we learned about differential equations? The solution is another equation, specifically what I always call, that's not a very good term probably, but the original equation. Right? In other words, if you've got a differential equation that's got y prime in it, then the solution is y equals. And that y equals has to not have y's in it, or y primes are in it, it's just y equals with x's in it. Okay, so the solution is the original equation. And then we also learned that an IVP, an initial value problem is what? What's an initial value problem? Yeah, it's a differential equation plus an initial condition. And that initial condition allows you to find the C, right? Because when we do our original equation, it often involves some sort of antiderivative and there's some sort of plus C involved in it. All right, then we also talked about 3 types. Now this is my definition, my definition of 3 types. There's a lot of types of differential equation that you would study in the differential equation course. But I identified them this way. Ones we can solve. Give me an example of a differential equation that we can solve. Give me the whole differential equation.
F of x equals x.
No, that wouldn't be a differential equation because it doesn't have a derivative in it. How about y prime equals, and just to make it interesting, let's put like a 3 in front of it or something, but yeah. Something like that, it's got an x in it, right? It's got just an x in it. Y prime equals 3x. It's got a derivative in it, so it's a differential equation. Okay? And so what would be the solution to that? Y equals 3/2 x squared plus c. Yeah, not 3, that would be y double prime. But 3/2 x squared plus c. That's the solution to that differential equation. Now, if we made it an initial value problem, if I would have stuck on an initial condition like say y of 1 equals 2, if I would have stuck on an initial condition to that, we could now plug that in and we'd have 2 equals 3/2 times 1 squared plus c. We'd have c equals what? 1/2, 2 minus 1.5. This would be 2 minus 1.5, would be 1/2. So we would have an equation of y equals 3/2 x squared plus 1/2. Now, that would be our, we call this a general solution, we call this a specific solution or a unique solution or whatever. So we have our general solutions. If it was an IVP, if it had an initial condition, we could find the C. Okay. So there were those that we could solve and so forth. Then we had the one that we memorized. Actually, there was 2 of them we were supposed to memorize. One is y prime equals k times y. Now that's not one we can solve because that's got a y in it. That's got the output variable in it instead of the input variable. And so we just memorized that solution was y equals ae to the kt. We just memorized, supposed to have just memorized that. So like on the quiz, and that might show up on the quiz. I mean, we're going to talk about differential equations more tomorrow, and I might give you one like that. You need to recognize that that is one, that you know the solution to, so you can then work with. Then the other one we had was Newton's law of cooling, which was similar. Newton's law of cooling looked like that, and then it was y equals t plus ae to the kt. So those were the 2 that we said we'll just memorize those solutions. Now, we will learn in Chapter 7 how to solve these differential equations. Those are called separable differential equations. If you ask a college person who's taken a class in differential equations about the types of differential equations, they wouldn't break them down like this. They would talk about separable differential equations. They'd talk about Wronskians. They'd talk about Bernoulli, and they would talk about all kinds of different types of differential equations. You have to identify them as different types so you know how to solve them. Kind of like we have a way to solve linear equations, we have a way to solve quadratic equations, we have, you know what I mean? So, different types of differential equations require different techniques of solving. All right, anyway, third one was the ones we can't solve. Now, we did some t-charts and things like y prime equals 3x y minus 2y double prime or, whatever. Something. We can't solve it. I think it could be solved, possibly, I don't know. It's been a long time since I took differential equations. But anyway, there's a group of those. Yeah. All right. So that's something we talked about there. All right. Then in a later chapter, I think it was in chapter 4, so we had talked about this back in chapter 2, I think, or even late chapter 1, I don't remember. I think it's chapter 2. Then in chapter 4, we talked about slope fields. Slope fields. Okay, now what we're going to do tomorrow is connected to slope fields. All right? Slope fields were a graphical approximation for the solution to a differential equation. A graphical, so now you can kind of see a little bit of how this is going to connect to what we've been doing in this chapter. It's an approximation to the solution. Just like left, right, trapezoid, midpoint, Simpson are approximations to the area under curve. They're approximations of an integral. Slope field is a graphical approximation to the solution of a differential equation. So, for example, let's take this differential equation right here. Now, I realize this is one that we already know how to solve, but let's just do that one. And let's draw ourselves a simple little graph. We won't put very many numbers on it, but we can do a couple here. And we drew some of these by hand. Now, you're not going to have to draw out a graph, a slope field by hand. We already did a quiz on that. And remember, we did some matching exercises and so forth. So if we label this a little bit here, okay, and if you remember, we had some dots. You know, it worked nice if you had kind of some dots on your paper, you know, that kind of thing. How did we draw a slope field into our differential equation? Let's imagine for a second that this was not one that we knew how to solve already. So but what we could do is plug numbers into this, and that would give us slope. So if I put a 0 in for x, I get y prime equals 0. That means the slope is 0. So 0 in for x, well, that's right here on the y-axis. So that just gives me these, that would just give me horizontal little strips right there, right? Now let's put a 1 in for x. We get a slope of 2. So when x is a 1, we'd get a slope of 2. So you put in these little lines like this. What about when x is a negative 1? Now then we get a slope of negative 2. So you get these lines, you know, and so we just estimated that. And if x is a 2, well, that's 4. Well, that's even steeper yet. Okay? And you can kind of see what developing there? Parabola. And that's because, of course, we know that if we do the antiderivative of this, we get x squared plus c. Now, if we had an initial condition in there, say we knew that y of 0 was 1, we would plot that initial condition, and then we would just kind of go with the flow here, and we would kind of see our solution curve in there. Now, again, as an exact solution, this is pretty rough, right? I mean, if we can solve this and put in our initial condition, we know it's y equals x squared plus 1, but if we can't solve it, then going with the flow is pretty inexact. Right? I mean, we're just kind of taking our pencil. So if you took individual points, if you had some really well-marked graph paper and you just went with the flow of your slope field and then looked at these points and said, hey, what's the point on the blue curve at 1.3? Right? You go 1.3, oh, it's about, you know what I'm saying? I mean, that y value would be pretty rough estimate. Much like 3 left rectangles is a pretty rough estimate, right? So how can we make that better? That's what we're going to talk about tomorrow, okay? What if we had a differential equation with an initial condition and we couldn't solve it? How could we get a little better approximation of some of those y values? Because that's what a solution is the original equation, the original y values. And so we're going to talk about that. Okay, and so that's kind of the connection to what we were doing, or what we're doing here in Chapter 6. All right, so anyway, that'll help us get started tomorrow, and then we will be able to give you some time to work on some of those things. So the rest of today is going to be working in packet sample 3. Sample 3. Now, what I would like for you to accomplish in that packet, at this point, hopefully you've gotten up to number 14. That was the goal the other day. The first section is no calculator. The first 28 problems are supposed to be no calculator. So if you got up through number 14, what I would like you to do for tomorrow is get to number 28, finish that section. See if there's any in there you don't know how to do, you can ask about. There might be some we haven't learned about. There might be some chapter 7 stuff that's in there. There are a few, I think, and see if you can figure out which ones those are. And then you can skip those. Then I also would like you to go to the free response section and do the first 2. The first 2 in the free response section, we should be able to do both of those. Okay? And that is your assignment for tomorrow. That, keep working on your Niobrara stuff that's due on Thursday.